Okay, so we've talked about tables a bit and getting frequency from relative frequency from the tables to get probability. So that's great for one variable. Now let's talk about two variables and contingency tables. This will help us get at something very useful called conditional probability. So this section is complex and conditional probabilities. So we talked about this a little bit already. We talked about intersections and the upside down U, A and B. And if you remember Venn diagrams, we're going to have pink here be the A and blue here be the B. And this kind of purpley football in the middle is the A and B. So that's where they overlap. And notice that things in there count for both. That's important. We also have an OR idea, A or B, and that's denoted with the regular U, which stands for union. And so here we have A and here we have B, and they don't overlap at all in this case. And so A or B could be just everything over here in A and everything over here in B. So for the ands, only being in both outcomes satisfies the condition. So remember, we had like 1, 2, and 3 for a dice roll, and 1, 3, and 5, and only the 1 and the 3 counted as being in both. Okay. If two things have nothing in common, or if they are defined as mutually exclusive, there is nothing in common, and the probability of A and B equals 0. Okay, so on a dice roll, for example, if probability of A is an odd number and probability of B is an even number, the probability of A and B together is 0 because you're not going to get both. Okay. If two things are independent, the probability of A and B is the probability of A times the probability of B. So if, for example, we want to talk about, again, A is 1, 2, 3. Let's write that out. So probability of A is the probability of 1, 2, 3, and that is 0.5. And then say we rolled, now let's say we toss a coin. So then the probability of B is going to be the probability of getting a heads. Okay, so what happens on the dice doesn't make any difference to what happens with the coin. And the probability of heads is also 0.5. So the probability of getting a 1, 2, or 3, an A, and getting a heads, okay, is 0.5 times 0.5 equals 0.25. All right. Now, why is that? Because you could get a 1, 2, 3 and get a tails, right? And that would be 0.5 times 0.5. You could get a 4, 5, 6 and a heads, and that would be 0.5 times 0.5, etc. All right. These two things, mutually exclusive and independent, are easy for people to confuse at the beginning, so make sure that you keep those separate in your head and go back to the definitions. For OR things, either outcome satisfies the condition. So again, we denote this as the probability of A or B, and that is the probability, go back, probability of A plus the probability of B minus any overlap. Okay, this is an important bit. Why do we subtract that part? And the reason is because it can get double counted. Like here, that part is both in A and in B. Here, there's no overlap, right? So, so the A and B would be 0, so we don't have to worry about it. So let's look at that in another example. This is a basketball championship example, the Atlantic Coast Conference. ACC, um, versus the Southeastern Conference, SEC. And we're looking at 20 years of data and whether they have had a team in the championship. Okay, so the ACC has had a team in the championship for 10 out of those 20 years. All right. And the SEC has had a team in the championship for 8 out of those 20 years. But in one of those years, they were both in those championships. Okay. So, what that would look like in our Venn diagram is we'd have um, ACC over here, and we'd have SEC over here. Okay. And the overlap would be 1. And the SEC was in there 8 years, but one of them, they were in there with the ACC, so that was 7. And the ACC was in there 10 years, but one of those years was with the SEC, so there are 9. And now you can see that the total ACC is 9 years plus 1 year equals 10. And the total SEC is 7 years plus 1 year equals 8. Okay, so 9, 10, that accounts for 17 years out of 20 total. All right. So we could say the probability that at least one of them would be in the championships was actually 17 out of 20, okay, which is 0.85. But let's do it with our formula, okay? So the probability of A is 10 years out of 20 is 0.5. And the probability of B is 8 out of 20, which is 0.4. And the probability of both is 1 out of 20 is 0.05. So we're going to subtract 0.05. So 0.5, 0.9 minus 0.05 is indeed 0.85. So that's the probability that ACC or SEC, that is at least one of them, is in the championship. Probability of neither is the complement, so the probability of ACC union SEC complement is 1 minus 0.85 equals 0.15. Sorry, that's sloppy. 0.15, which is indeed the 3 years that are left over. If we did it that way, the 3 years that are left over divided by the 20 years. Another thing that's important in this section is looking at conditional probability. This is a key idea for examining group differences. The idea being, does knowing something about one variable tell you something about likelihood of the other variable? So if you know something about one group, like the ACC group, does that tell you anything about how they do on something else, like being in the championship? And indeed, in the case above, it did, right? Because they had different probabilities of being in the championship depending on which conference they were in. So that gives you a conditional sort of idea. So conditional says, what if we know some information? And the notation for this is the probability of A given B. And the given is the up and down slash. B is the information that we already know, and A is our new assessment of the probability of A, given that we know B. There is a short Bayesian formula for this as well. Think about the probability tables that we made back in the previous chapter where we had the joint probability inside the body of the table. That would be like an A and B, right? The value on one thing times the value on another thing at the intersection. So if we take that and then divide it by the marginal probability of the given thing, B, right? That gives us the conditional probability. So sometimes it's easy to figure from the table, sometimes it's easier to figure out from probabilities, depending on what you're given. So here's an example. Teams and cola preference. I was out in Minnesota when I first developed this. And so, of course, Minnesota Vikings fans, right? But their arch nemesis was the Green Bay Packers. And so, one of the things that teams might be interested in, and you might notice this if you go to professional sporting events, some of the some of the venues, the arenas and things have maybe Coke, and other ones have Pepsi in the vendors. And so they might do that based on what the cola preferences were for their particular team. Okay. So we could ask, well, all right, if you're a Green Bay fan, do you prefer Coke or Pepsi? And if you're a Vikings fan, do you prefer Coke or Pepsi? And if you look at this table, just we've got 10 people in each team here. And so for the Packers, and I'm going to switch colors here for a second. Hold on. I'll switch to blue. There we go. For the Packers, from those 10 people, they prefer Pepsi, right? There's 8 of them in the Pepsi column and only 2 in the Coke. But for the Vikings, they actually prefer Coke. It's not as strong a preference, but they do prefer it. Okay. Overall, if we knew nothing about which team you were in a fan of, overall, people prefer Pepsi. So if we knew nothing about team, we would expect you to prefer Pepsi. But if we learn which team you prefer, aha, you're a Vikings fan, then all of a sudden we expect you to prefer Coke. All right. So now let's put some numbers to this. So the probability that you're a Green Bay fan is 10 out of the total in this sample is 20. So that's 0.5. Okay. By the way, that's also the probability that you're a Vikings fan. Probability that you're a Coke fan is 8 divided by 20 equals 0.4. Okay, which means the probability that you're a Pepsi fan is 0.6. Probability that you like Coke and Green Bay is 2. That's this 2 up here. Divided by 20 equals 0.10. But what about the probability that you like Coke or Green Bay? Okay, now that gets a little bit more complicated because there are 8 people that like Coke and 10 people that like Green Bay, but 2 of those overlap because they like Coke and Green Bay. So for this one, we're going to use our formula. So the probability that you like Coke, we said, is 0.4. The probability that you like Green Bay is 0.5. But we've got an overlap of Coke and Green Bay, and the probability there is 0.1. So 0.4, 0.9 minus 1 is 0.8. And if we added those up only once, right, that would be 2 plus 6 plus 8 equals 16 divided by 20 equals 0.8. We could do it that way too. Notice that we only counted those 2 one time. Now, what's the probability that you like Coke given that you're a Green Bay fan, right? It's not very high. We could do this directly. So we could say probability of Coke given Green Bay, because we've got the table, is 2 people who like Coke out of the Green Bay fans. Out of, now we're given that you're a Green Bay fan. And once we're given something, that means we're only allowed to look there. Okay, so we're only going to look here because we're given Green Bay. All right, and so that becomes our new basis And there are 10 people in that condition that we're given. So we're going to take the 2, but we're going to divide it by 10, and that is 0.2. We can also do it using the formula. So the probability of Coke and Green Bay we figured out is 0.10, and the probability of Green Bay we figured out is 0.50. Okay, and so that basically is 1/5 is 0.20. So if you have the whole table, you can do it with the table, but if you don't, you can also do it with the probabilities, and you should practice both. If we convert this to a joint probability table like we do in R, then we've got all of these interior probabilities. So where is my pen? There we go. Block these off. So these are joint probabilities, okay? And notice 1, 4, 8, 10, those add up to 1. These over here and down here are marginal probabilities. They also total 1. So these totals are unconditional probabilities. And to get the conditional, so like the probability of Coke given Green Bay, like we just did, you take the joint probability of the 0.1, and divide it by the 0.5. So again, probability of Coke given Green Bay equals the 0.1 joint probability divided by the 0.5, using the formula in the previous slide. So we can do it by inspection, or we can do it with the formula. This allows us, remember we said before, are events independent, and that's different from whether they're mutually exclusive. So this gives us a way to define if they're independent. If the probability of A given B is the same as the probability of A. In other words, knowing B doesn't tell you any information about what's going to happen with A. You can also reverse that, and it works the same way. Then they are independent. Okay, so they are independent if the probability of A given B is equal to the probability of A. So in our problem that we just did, the probability of Coke given Green Bay is 0.2. And so the question is, oops, so we have a question, is that equal to the probability of just Coke? And the answer is no, because the probability of just Coke is equal to 0.4. So these are not independent. Indeed, when we very first looked at this, we said, oh, yeah, which cola you like depends on which team you like. They are related, not independent. That's it.